Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on nonlinear control systems. Today we are going to start a new topic, which is called adaptive control. Adaptive control is being discussed as a single topic in this course. However, in reality, adaptive control is such a vast topic that there are separate courses being offered across the universities in the world on adaptive control, and we shall be discussing this as just to get the flavor of this type of control systems. Okay, so let's start with a motivating example about the adaptive control. Consider a scalar system, x dot equal theta x plus u, where you have x is the single state variable and its derivative depends upon x itself multiplied with a constant theta, but here the problem is that theta is unknown. We know that it is some constant, but we do not know the value of theta. So x is a state, u is control variable, and theta is unknown fixed parameter that we do not know the value of. So our goal is to drive the state to 0 as time goes to infinity, so which is to basically asymptotically stabilize this system with the help of our control input. But here the new thing is that we do not know, there is an unknown parameter theta in the system. So we have to achieve this goal despite the presence of an unknown parameter in the system. So all we need is basically what in normal cases what we do for such systems is that we have u is equal to minus kx, and then minus x, additional minus x is such that we hope that k would minus kx would cancel out plus theta x, and then there will be additional minus kx to drive the dynamics of x of t to 0 as t goes to infinity. So this will achieve the asymptotic stability for the above system. But if if theta is less than 0, then any k would work, because if theta is less than 0 we don't even need this control input. X dot equals to minus x minus some constant times x, that is already asymptotically stable differential equation, and even k is equal to 0 would be fine. But what if theta is greater than 0? So if theta is greater than 0, then what we can do is that we can start with the small value, because theta, we do not know theta, it could be large, it could be small. So what we do is we start with a small gain, and then we keep on increasing the gain value, and we hope that at some point the gain value will be equal to or greater than the value of theta, and at that point this type of gain would basically render the system asymptotically stable. So this you can see that we are basically tuning the gain here. So we are trying to change the gain as we implement the control. So k must be dynamics. K must be dynamic. So let us define some dynamics of k. We know that the dynamics of k should be such that the k should be increasing with the passage of time. So just for the sake of defining it, I define k dot equal x square. So there is some intuition behind this, because x square has certain properties which are desirable. For example, when x is close to 0, then x square is so the k will grow slowly when x is close to 0, which means that we will avoid the issues of overshooting or chattering type of issues. And then when x is far away from 1, then k will grow fast. So these are some good properties that we obtain with this gain tuning or gain dynamics. So later on we will call this the tuning law, because this is basically changing the gain of our controller. This K is the gain of the controller, and we are changing the gain of the controller with the help of this dynamical equation. Okay, so now the question is that if we implement u equal minus k plus 1 times x, where k is a dynamic variable driven by this differential equation, would this be enough to stabilize this system regardless of the fact that we do not know the value of theta? So let's try to answer this question. So I copy the dynamics and I copy the tuning law and the control equation, and the question is that is u an asymptotically stabilizing feedback control for the system with unknown parameter or not? So let's look at this solution that we define. We use the Lyapunov function approach to prove the asymptotic stability for the closed loop system. We define the Lyapunov function as so we assume that x and k are the states of the system, and the Lyapunov function is defined as x square by 2 plus k minus theta square by 2. Here we cannot use any value for theta, we just putting it there because you will see in a short while why I have put theta in the Lyapunov function. But remember that theta, we do not know the value of theta. The only thing we know about theta is that it is some constant. So if it is some constant, then putting it in the Lyapunov function does not violate any rules related to the Lyapunov function. This Lyapunov function is positive definite, and when I take the derivative of the Lyapunov function with respect to time using the chain rule, so x square by 2 derivative becomes x times the derivative of x, and k minus theta square by 2 derivative becomes k minus theta into derivative of k minus theta, which is with respect to k, which is simply 1, and multiply by k dot, which is x square. So this is the v dot equation, and then if we simplify v dot, then you can see that theta minus k here and k minus theta here both are multiplied with x square, so they cancel out, and only thing that remains is minus x square. So minus x square is less than 0 for all x, and that is all we want. We do not care about this state k. It can go anywhere. We don't have any control objective of driving k to 0. So this Lyapunov this result is good enough for us because we are only looking at the stability with respect to x. Although this whole system as a whole will not be asymptotically stable with this kind of result, but this result is enough to show us that at least your state x will go to 0 as time goes to infinity, which is basically our control objective. So since we only need asymptotic stability for x, the above analysis indicate that we have our desired result. And note that we do not need to drive k to be equal to theta, or we do not need to know the value of theta in order for this result to be valid. Whatever theta is, it just cancels out in the mathematics, so theta it does not affect any the stability property with this type of control. So I plotted this with some initial conditions. So this differential equation, if you plot this differential equation with the control law in the MATLAB, I gave the initial conditions x of 0 to be 5 and k of 0 to be 0, and theta value I chose to be 5 just for the sake of example. And then the result is that your k keeps on increasing and it settles down at certain value, while your x goes to 0 as t goes to infinity, which we predicted here that x would be asymptotically stable, and we have it. Alright, so let's try to summarize what we have learned from this example. So first of all, we have learned that adaptive control is used for systems where we have unknown system parameters. You all know that there are modeling uncertainties in the systems. So this unknown parameter could be representing the uncertainty in the model. This could also be representing the disturbance, process noise, and many other things that would disturb the dynamics of the system. So first of all, we have learned that adaptive control is used in such systems where there are some unknown parameters. Second thing that we have learned about adaptive control is that the gain of the adaptive control is not fixed. But the gain of the adaptive control is such that there is a gain tuning law involved with the gain, which becomes part of the state while doing the stability analysis. So the gain of the adaptive control, as the name suggests, the gain adapts. So the gain is adaptive and there is some adaptation law behind the gain. The third thing that we have learned is that in a well-designed adaptive control, the gain would adapt for some time. There will be a transient state of the gain adaptation, and then eventually the gain will settle down at some value. So the steady state gain would always be a fixed gain, and the system would be asymptotically stabilized by a well-designed adaptive control. So these are the three main driving factors. Adaptive control is used where the system has some unknown parameters. In adaptive control, the gain basically adapts according to a tuning law, and in a well-designed adaptive control, the gain will, after some transients, settle down to a steady value, and the control objective will be achieved. Okay, so this result we have plotted for theta equal 5 and initial conditions, x naught equal 5 and k naught equal 0. Let's try to plot some more results. For example, this result I have plotted for theta equal 5, but initial conditions are small. So initially x naught is less than 1. So when x naught initially when x is less than 1, then x square is even smaller. So you can see that the transient in the initial phase, the adaptation in the gain is very slow, and then it picks up pace as the x increases, and it increases beyond the value of 1. Then x square becomes a larger number, and the gain adapts slowly in the beginning and then fast adaptation, and then it eventually settles down. Okay, so there you have, there is some impact of initial conditions on the performance of adaptive control. And another example, I made the initial condition, I kept the initial condition as the same as this one, but I changed the value of unknown parameter theta. If the unknown parameter theta is 0 instead of 5, you can see that the value at which the adaptive control gain settles down is just over between 0.1 and 0.15, but here the value is 8. So there is a huge difference in the steady state value of the gain of adaptive control, and all of this is being done automatically. I am not selecting this steady state value of the gain. This control law and this whole dynamics are automatically selecting this based on whatever value of theta it turns out to be. And similarly, if you plot for theta equal -5 with same initial conditions, then the gain, the steady state value of the gain is not even 0.1, it is way less than 0.1. So you can see that the steady state value of the gain is decreasing in this case with the value of theta. Of course, if we increase the value of theta beyond 5, the steady state value of the gain would increase. And this we can also see here from this equation, that if theta is 0 or negative, then a very small control, and for negative theta even zero gain would be fine, but we have just a little bit more gain than the 0 here. Okay, so this is the adaptive control simulated under different initial conditions and different values of the unknown parameter. You can also plot the same equations in MATLAB using ODE 45 function, built-in function, and see what happens for other initial conditions and other values of theta. That will give you more insights into the adaptive control. Okay, so there is the concept of adaptive control. So what happens in adaptive control is that you have a feedback control where you have a controller and a plant, but the difference is that this adaptation of the gain, you have you take the output. In this case we took the value of x and use this value of x in the tuning law, and the tuning law basically gives the input to the controller regarding the change in the gain. So the gain changes due to this adaptation. So this is the conceptual block diagram of adaptive control, where there is normal feedback control augmented with the adaptation law or the gain tuning law. Okay, so let's look at the general case for scalar systems. So consider a scalar system x dot equal ax plus bu, where we do not know a and b. So a and b both are unknown parameters, but at least it should be known about b that b should not be 0. If b is 0, then we have no control. So it has to be that b, even though we do not know the exact value of b, at least we should know that b is non-zero. So if a and b are unknown, then the following adaptive control shall asymptotically stabilize the given system. The tuning law is the same as before, and the control is u is equal to minus kx. So this result can be implemented on any first order systems of this form with unknown parameters. If you implement this tuning law and this feedback control, you will have an asymptotically stabilizing system. So k dot equal x square is called the tuning law. Okay, so let's try to extend this adaptive control for systems of higher order. So in this case I have introduced the integrator state, which is x dot equal theta x plus v, and v is the state such that the derivative of v is the control signal. So v is called the integrator state. So in this case you can still design the adaptive control, but it will become a little bit more complex than the first order or scalar system. For such system, the adaptive control you can use is u is equal to minus x minus k dot x plus k plus 1 times kx plus v minus v plus k plus 1 times x. So I understand that this is a fairly complex control law compared to the control law of u is equal to minus kx, but this is what we have for so introducing the new state in the system. So here we have k dot equal, so adaptation or tuning law also changes for this type of system, and it has two terms. First term in this tuning law is the same as before. We had k dot equal x square before for the first order system, so we have k dot equal x square again, but there is an additional term added here, which is v plus k plus 1 into x multiplied by k plus 1 into x. And this is the additional term for having an additional state. So you can notice that the tuning law is of the form tau 0, which is x square, and tau 1, which is this whole term. So tau 0 is just x square and tau 1 is this whole term. And the asymptotic stability for this control law using this tuning and this system can be proved using this type of Lyapunov equation, but Lyapunov function, but we will not go into the details of that. You can see the details of that in any standard textbook on adaptive control, and I will also provide references at the end of this lecture where you can see the proof of asymptotic stability if you are interested. So this type of so here we have adaptive control for the system, second order system, where we still have only one unknown parameter theta, but we have two states in the system, and the control law can be designed like this with the adaptation tuning law of this form. So let's try to simulate this. So these are the dynamic copied on the next slide. So x dot equal theta x plus v, k dot equal this whole equation, and v dot equal u, and u is equal to this whole expression. And when we simulate this whole feedback control system into MATLAB, you can see that with the initial conditions of x equals 0.5, v equals 0.5, and k equals 0, and unknown parameter theta equal 1, we have this type of dynamics where k starts with 0 and it tries to adapt, and then it settles down to a certain value. And meanwhile the state variable x has its own dynamics and it settles down on 0, and the other state variable v has its own dynamics and it settles down on 0. So the system x and v, the second order system, is asymptotically stabilized while the gain is adaptive according to this tuning law. Okay. So we can have another result for same initial conditions but a quite large value of theta, and you can see that for a for theta equal 10 compared to theta equal 1, the results are quite disturbed. For example, there's a lot of vibration in the variable v here, and there's a lot of vibrations in the control law as well. And but finally, as predicted by the theory, this system is asymptotically stabilized. But this does indicate that we may have some problems for larger values of the unknown parameters. So adaptive control can cater for uncertainties, but if the uncertainties are very large, then adaptive control performance may begin to deteriorate. But for small uncertainties, it works very well. Okay, so next we are going to look at the model reference adaptive control. So far we were looking at the system with unknown parameters, and now we are trying to look at something different, which is we have a reference model, which is, this model indicates how we want our plant to behave. So we want our plant to behave like this model. We have this model as a reference, and we apply the same input R to our feedback control system. So this is the adaptive control system: controller plus plant plus adaptation. So this three blocks, this is our adaptive control system applied to this plant, and this is our reference model. This is how we want this adaptive control system to behave like. So we want this adaptive control system to behave like this reference system. This is the problem of model reference adaptive control. So how do we do that? Notice that this plant could be quite different from the reference model itself. So these two systems are different, but we want this system to behave like this system using the adaptive control. So we apply the same reference to the adaptive control system and same reference to our model, and whatever output our model generates, we want this output to be same as, we want y to be equal to ym. So how do we measure the performance of this model reference adaptive control? We want to drive the difference between y and ym, which is E, we want to drive this E to 0 using this adaptive control. So the purpose of adaptive control here is to drive this variable E, which is the difference between ym and y, to 0. Okay. So we want the closed loop system to reproduce the input output behavior of a given reference model driven by a reference signal R. Okay. So we can consider a scalar plant y dot equal a b plus bu, y dot equal a into y plus bu. Here this should be y, so I just correct it because this is okay. So this is what it should be, y dot equal ay plus bu, and then a is completely unknown and b is unknown, but at least there is an L missing here. It is not at east, it is at least. At least we know that b is greater than 0. So before this we assume that we do not know b, but at least we know that b is non-zero. Here we are going to take this assumption a little bit further, that we know that at least b is greater than 0. We don't know the value of b, but at least we know that b is a positive number. And about a, we do not even know whether it is positive or negative or 0. We do not know anything about a. And on the other hand, we have a model system where ym dot equal minusamy plus bmr. Here we know exactly what am is and we know exactly what bm is, because this is our model system. This is the system according to which we want this system to behave. This is an unknown system, this is a fully known system, and we want this unknown system to behave like this fully known system. So how do we achieve that? So we are trying to achieve that using the control law. Here we assume that the am is greater than 0, so that this system is asymptotically stable, and r is some signal with Lebesgue space of L infinity space, which means that r has finite infinity norm. It is a finite signal, and some smoothness properties are present in this signal. So these are very standard signals. So we have this type of situation. For control, we use combination of feed forward and feedback. And how do we use the combination of feed forward and feedback? We define the control law u is equal to minus k times y plus L times r. So this is the feedback term, and this is the feed forward term, which is basically depending upon the reference value. So this is our control law, minus ky plus lr. Okay, if we use this control law, then y dot will become a minus bk times y and plus bl times r. But to match this model with y dot equal minus am into y plus bm into r, we need a minus bk to be equal to minus am. If this a minus bk becomes minus am, then, and also if this bl becomes bm equal to bm, then we have this system will become identical to this system. So we need these two equations to be satisfied. So this equation gives us the value of k equal a plus am over b, and the second equation gives us value of L, which is another control gain, to be equal to bm over b. So this has, so we have almost designed control law, which gives us, which renders this system to be equal to this system using this control law. But as you remember, there is a problem in this control design, and the problem is that we do not know the value of A and we do not know the value of B. So A and B are appearing in the control law, and we cannot implement this control law because we do not know the value of A and value of B. So that is the problem. So we have to find another way. So what other ways can we use? Instead of using these K and these L gains, we can use the estimates of K and estimate of L, which we hope or somehow we try to make them in such a manner that they become very close to or equal to these type of values, and then this system will behave like this model system. But how do we achieve that? So where K hat and L hat are the estimates of K and L, and there are two ways of achieving the K hat and L hat. One is called the direct model reference adaptive control, and the other way is called indirect model reference adaptive control. We shall be looking at both direct and indirect methods in this lecture. So let's first look at the direct model reference adaptive control. So we have a system y dot equal y dot equal ay plus bu, as I have corrected in the previous slide, and y m dot is, so let me just, okay, so the correction in the equation, sorry about that. Okay, so we have y dot equal ay plus bu, and the model, the reference model y sub m dot equal minus a sub m y sub m plus b sub m into r, where r is the reference signal. We have a control law where we have gains, the estimate of the gains, and one is a feedback gain and the other is a feed forward gain, and then we have the following tuning laws. So let us use the K hat dot, the tuning law for the gain, for the feedback gain, as minus gamma times the difference between ym and y multiplied by y itself. So gamma is some positive tuning parameter. You can select gamma to be any value as long as it is greater than 0. Similarly, another tuning law is for the feed forward gain, the tuning law is gamma times the difference between ym and y multiplied by the reference value r. Okay, so gamma is positive, and this reference tracking control, this control basically you can prove using the Lyapunov function approach that this controller achieves ym equal y asymptotically. So asymptotic, by reference tracking, I mean that the tracking of this y is trying to track this reference y. So in this situation, the reference tracking does not mean that we are trying to track a reference signal value, but here we are trying to make the output of our original plant to track the output of the model system. So in this case, reference tracking would mean that the output of our adaptive control feedback system would track the output of the model system. So reference tracking would mean that y will approach ym. So this can be proved using the Lyapunov function, and here are some simulation results with these conditions. So I have selected gamma to be equal to 2, am to be 3, bm to be 2, and unknown parameter a to be 5 and unknown parameter b to be 1, and the reference r signal to be 2, and initial conditions for y 0.5, for ym 0.02, for k hat and l hat initial conditions are 0. And you can see that here this blue signal is y and green signal is ym. So y, after some transients it does actually converges to the ym. So here we have reference tracking, and The gains, they have some transients. So this is the k estimate gain, k hat. It has some transients and it finally settles down to a steady state value. Similarly, L hat has its own transients and it eventually settles down to a steady state value. So this is model reference adaptive control using the direct method. Direct method means that we are directly estimating k and L using the tuning laws that involve k hat and L hat. So our tuning laws are directly based on the gain values. This is what we mean by direct model reference adaptive control. So direct model reference adaptive control, what do? We have a model system, we have the actual system, we define the gains, and we have tuning laws, and then that tuning law and this control law combined with the tuning laws renders this adaptive feedback control system to behave like this model reference control system. Okay. Then we have indirect model reference adaptive control. We have the same unknown system, y dot equal ay plus bu. Okay, and then we have the reference system, y sub m dot equal minus a sub m y sub m plus b sub mr, and then we have the control law. But here we go back to the equations that we derived for the control gains, and we saw that this control gain was a plus a sub m over b. Instead of, because we do not know a and b, we replace the a and b with the estimates of a and b, and similarly here we replace the b with the estimate of b. And then the tuning laws are not in terms of k hat and L hat, the tuning laws are in terms of a hat dot and b hat dot. So then the tuning laws are very similar. So for a hat dot, the tuning law is minus gamma times y m minus y times y, and for b hat dot, the tuning law is gamma times y m minus y into r. And if you use these tuning laws, then you have here, instead of direct adaptation in k hat and L hat, you have indirect adaptation in the parameters of which the L hat and k hat are function of. So k hat and L hat are functions of some parameters, and you are adopting the parameters within the gain, you are not directly adapting the gains themselves. That is why it is called indirect method for model reference adaptive control. Gamma is once again a positive constant, and the proof of reference tracking is not discussed in this lecture, but we do discuss the simulation results. You can see that here I have simulated the system for gamma equal 2, am equal 3, bm equal 2, unknown parameter a equal 5, the other unknown parameter b equal 1, and the reference value 2. Initial conditions, I have taken y and ym to be equal to 0.5 and 0.2 respectively, and a hat, the initial condition of a hat I have taken to be equal to am, which is 3, and the initial condition of b hat I have taken to be equal to 2, which is bm. So am and bm are known, so we take the initial conditions of a hat and b hat to be equal to am and bm. This is just an intuitive action, something I have done with the help of intuition. Okay. The results here are quite nice, because your output y of your given system, it after some transients it converges to the output ym, and similarly your gains, these are not the gains, these are actually the parameters a hat and b hat. A hat and b hat after some transients settle down. So the settling of a hat and b hat means that actually the gains will settle down at the corresponding values that can be calculated using the values of a hat and b hat in this graph. overall, you can see that we have implemented the model reference adaptive control using the direct and indirect approach, and both approaches do give us some good results. And you are welcome to simulate these equations with some other initial conditions and see what happens when you increase or decrease some initial conditions or values of unknown parameters. So that would be a good learning experience for you. And before I end this lecture, I want to acknowledge the references that I have used. Mainly I have used the results discussed in the class notes of Daniel Liberzon from University of Illinois Urbana-Champaign, and this is the link for his class notes. You can also access the notes using this link. And another good resource is the lecture notes of Anuradha Annaswamy from MIT, and she has the whole course material. She offers a whole course on adaptive control. This, by the way, is also this is a full course on adaptive control, and Anuradha Annaswamy also offers full course on adaptive control, but we are discussing adaptive control just as a single topic in our course on nonlinear control systems. So if you are more interested to know more about adaptive controls, these two resources are highly recommended, and there are some resources that are mentioned within these resources. So you have plenty to look at in terms of adaptive control. And we have in this lecture only looked at the tip of the iceberg. We have just got the flavor of the adaptive control. This lecture will not make you any expert on adaptive control just in itself. But if you have got the flavor, you have got the concept of the adaptive control, you have got at least one method in the adaptive control, which is model reference adaptive control, and the other method, that is how to control the scalar and second order systems using adaptive control. And then that is it. That is the end of lecture, and I would like to summarize the whole lecture in a couple of minutes at the end, as I always try to do. Okay, going back, and so we started the discussion of adaptive control with a motivating example of a scalar system where we have only one unknown parameter theta, and we wanted x to go to 0 as t goes to infinity, and the problem is that the theta was unknown. We tried to design the controller in such a way that this control gain, we basically said that the intuition is to start with a small control gain and keep on increasing until it becomes large enough so that the system becomes asymptotically stable. And it turned out that the intuition was a good one, and it results into an asymptotically stable system, for which we proved the stability using the Lyapunov function. But the stability was proven only for the state x, not for the state k, and that is good enough for us because we only need the x to go to 0. And we also looked at some simulations. Here the value, the initial condition of x is 5, so there is a fast adaptation right from the beginning. But if you take the initial condition to be smaller, then in the beginning the adaptation will be slow, and then it will become fast, and the gain will settle down to some value. And we looked at different initial conditions and different values of theta, and we saw that for smaller or negative values of theta, the gain converges to a smaller steady state value. And this is the whole concept of adaptive control, that we have adaptation using the tuning law. Here we have tuning law k dot equal x square. And then we looked at general case. So for general case, we have the same tuning law, k dot equal x square, and u equal minus kx would asymptotically stabilize this system, where a is completely unknown, but about b we at least know that it is not equal to 0. and then k dot equal x square is called tuning law. Then we have extension of the system for state with integrator state, and then we looked at that, and it showed that we have some in the tuning law we have the previous term and then a new term, and the control law becomes fairly complicated for this type of system, and we did not discuss the proof of this system, but you can look at the proof of this system in the references that I have provided at the okay. So next we look at the simulation results, and we saw that if the parameter value, unknown parameter value, is too large, then the behavior becomes a little bit clumsy. And then we looked at the model reference adaptive control, where we want this adaptive feedback control system to behave like a reference system. So we want the same reference for the adaptive feedback control law system and the reference system, and we want the output of both the system to be equal to each other. So we want this difference between the outputs to go to 0. And how do we do that? We have two methods. One is a direct method, where we have the tuning law that is before we looked at direct and indirect method, we just look at basic calculations and we see what we need, and we realize that we cannot have what we need, so we have to improvise. We have to find some other ways of getting this type of control gains. So what we do is we have two methods, direct and indirect. In direct method, we directly tune the estimates of the gain. Though tuning laws are involving the control gains, and when we implement that this gives us fairly good results with some initial conditions and values of the unknown parameters. And then we looked at the indirect method, where we do not tune the gains directly, but we tune the parameters that appear inside the gains, the unknown parameters that appear inside the gain. We tune the estimates of those parameters, and then we still have good results. It is recommended to compare the results from this slide and the previous slide for different values of the known and unknown parameters and different values of initial conditions. That will give you more insights into the adaptive control. Last but not the least, there are references. Daniel Liberzon from University of Illinois Urbana-Champaign, and Anuradha Annaswamy from MIT, Massachusetts Institute of Technology. And that's all we have for now. Thank you for listening. Let me know if you have any questions.